Oh, yeah.
All right. So my goal for today is to just mention naive Bayes, what it is, and give you guys a sense that it's possible and that we can do it. And we have some idea of how to do some easy examples with that. But I want to get to these example problems pretty quickly, just because in past tests we have asked very little about this, and we've asked a lot about interpreting Bayes nets. Now I haven't seen the test yet, so keep that in mind. But they tend to focus a lot more on this, so I'll go into this a lot more in detail. All right, so just review what we did last time. So we have some important equations that we talked about. So the first one was the joint. Let's see. Oops. So there's the equation for the joint. So it's the same as what we talked about last time. We also have, so this is joint. We also have the marginal equation, which I don't think they ever write a general case for it, but I like to write a general case like this. And so what I mean here, so you guys should be familiar with this one. So this is all the variables here that we care about. And then we can express that as a product of those variables given just their parents in our Bayes net. All right? And then here, we're talking about a subset of the variables. And here's the total set of the variables. So here's the total joint distribution. And we want the marginal. So we don't care about from C to D. We don't care about those. And so we can use these sums to kind of get rid of those for us. All right, then we also have the chain rule. And then from the chain rule, we can also get the Bayes rule. All right. And then what's really important to remember are the general methods. So if you have the general methods on some cheat sheet or something for the exam, you're going to be really well off. So let's just review what those are. So we have these equations, and we have our Bayes nets. And so, let's just give an example of a quick Bayes net. So we might have something like this. There's one. Just a quick note, they don't have to be connected. So there could be something like this on the side, and this is a valid Bayes net, all right? And so now we might be asked questions like, what is P of X? And if you remember, in here we have these condition tables. But what we have is, for each one of these, let's give these names. For each one of these, what we have is a condition table that says given your parents, what's the probability that this current node is true? Right, so A could be true or false, and then we might have something like 0.7 or 0.01 or something like that. Okay? And then the same is true for all of these, and so this one has like 2 parents, so this table's a little bigger. So this one's going to have something like A and B, the probability of B given A and B. And then it's going to have true, 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 false, false, true, false, false. And then some numbers here, all right? And so we have things like that. We have things like a node given its parents, right? A variable given its parents. And so when we want to ask a question like this, P of x, or some sort of marginal, so maybe P of xy, so not the entire set, but just 2 of them, how do we find out what that is? So it'd be really easy if we had x or y or something like that at the top, because then the parents, they don't have any parents, and it becomes a lot easier. But in the general method, what we want to do is we want to take that, which is going to be some marginal probability, and we're going to use this equation 2 to get it in terms of the joint probability, right? So maybe we have some other variables z or w that aren't part of that expression. So this is from equation 2. And then we're going to use equation 1. Well, here's the entire joint distribution. And now we can get things in terms of variable given their parents. And that's great because that's exactly what we have in these tables. So once we use equation 1, we'll be able to just read values right out of our condition tables. So now we can use equation 1, and we can get this sum of z w, and we'll get some product of some probabilities involving x and y and z and a bunch of stuff in here. So there's a bunch of math that goes into that, but we'll see how it's not actually that bad, because a lot of things will end up canceling out, and there's this rule about using the ancestor graph, which is the next step. So then here, we're going to use the ancestor graph. And we're going to be able to eliminate a lot of the terms that we get. So all this is follow rule 2, follow equation 1, use the ancestor graph to eliminate some of the terms in here, and then just solve. Okay? And that way you'll be able to get this marginal distribution, and you'll be able to read those values in here just from the table. Okay? And now there's one more thing that we have to be able to do, very similar, is we have to be able to compute conditionals. So something like x given y. Okay? And the approach is going to be really similar. All we're going to do is we're going to use the chain rule first to get that this thing, the x given y. We're going to solve for it, and we're going to get something like p of x and y over p of y. And each of these two pieces is just like what we just did right before. Those are just using equation 2, use equation 1, cross out things based off the ancestor graph, solve for py, and then you also do the same thing for solve for p of x and y. Take them and divide them, and then you can get this given. So these are just, this is just use chain rule first, and then solve for p of x and y using the general method, and then solve for p of y using the general method and divide them, and then you'll get p of x given y. Okay, that's a really quick overview of what we did last time. So if you guys want more review on that, I should have, I think the video is already up, but if not, I'll put it up tonight from what we did last time. Okay, so that's Bayes nets on probability review. So let's talk about naive Bayes. I'll also email out a link to some of the tutorial notes from a couple of years ago that describe the general method in detail. So I think someone was complaining that in the video they don't show up because I forgot to turn the camera or something. So I'll email that out too. So let me get my example. Okay. So in this example, we have East Campus, West Campus, and FSILGs. And we asked 10 people from each of these living groups some questions, and they filled out a survey for us. And so we asked them whether they think of themselves as a pyro, whether they're good with foreign languages, and then also whether they're in good shape. Okay, and so we actually got 10 people from each of these living groups, and so here's how they responded. 8 out of 10 from BC said they were pyros, 3 out of 10 from West Campus, and 1 out of 10. Okay. And then we also got these results. Three out of 10, and okay. Okay, so here's some data that we have. So you could probably, usually you represent this data as like kind of like a database where each row would have like, person 1 said that they were a pyro and that they didn't like foreign languages and that they weren't in good shape, and they said that they were from an FSILG, right? And so we have a bunch of these in our table, but we kind of just consolidated all that information into this, right? But presumably this is how we got the results back. And so now we'd like to be able to answer questions like, let's say a pre-frosh comes in, and what we're trying to do is we're trying to make an MIT sorting hat. So now a pre-frosh is able to answer this survey, and we want to fit them into one of these living groups based on their results. Okay. So we might ask, okay, so actually before moving on, just want to point out that this is exactly what a supervised learning algorithm does. So this is a type of supervised learning algorithm. Because what we're doing is we have a bunch of example training data in the form of the classification we're interested in is what dorm are you in, or what living group are you in, right? So this is like the Y. And then the features are like, did you say yes or no to this, yes or no to that, and yes or no to that. So X is like a 3-dimensional feature space, right? And so here we have our X's and our Y's, and what we'd like to do is, given some X, we want to compute our best guess for Y. That's exactly what a supervised learning algorithm is. So we had a lot of strategies for doing it before, but now we're going to use a probabilistic-based approach with naive Bayes. And so what we're going to do with naive Bayes is we're going to compute the probability for a given classification given the features. So this is an alternate notation. This is the same as in my notation. I write guess Y given X. Right? So all I'm saying is, what's the probability of this classification given that they answered this on the survey, right? Here C is classification and F is like the listed out features. So it's just like this vector expanded out. That's how they write it on a lot of the notes. So we'll use this notation. And so what we want to do is we can actually compute these with a little bit of some of those math equations over there. We can change this into something that we'll be able to just read off of this chart here and compute the probability that they are in, the probability that they match up with like East Campus, given like that they answered this on their survey, and then the probability that they want to be in West Campus based on the results of the survey, the probability that they should be in FSILG based on the results. And then what we're going to do is each of those will give us a probability, and we're going to choose the most likely one, the highest probability one, right? So what we're going to do, we're going to take the arg max over our classifications. So consider East Campus and compute this, and then do it again for West Campus FSILG. Take the max one. That's the one we want. So let's actually do that here. So let's see, what do they ask us? Okay, so let's say someone, let me do this over here. Let's say someone, let me turn the camera. Okay. Let's say someone answered that they are a pyro, that I'll use, I guess, L for foreign languages since I'm going to have falses and I don't want to confuse the F's. That they're not good at foreign languages and they're not in good shape. Okay. And so where should they go? And so what we're going to do is consider the probability that they're in East Campus, given these values. So here I'm using the notation where the bar on top means not, right? I'm going to compute all these three and then take the max. So how do I compute this thing? So it turns out that's something we can do. Let's see, where is, okay. So we can write out classification given some of this stuff, some of these features, as the probability of the classification times the probability of the features given classification over the probability of the features. So this is just using the Bayes rule to rewrite this. Okay. All right. Awesome. And then, yeah, okay. And then we're also going to use another trick, which is that in the numerator, we have this probability of the features given the classifications. And we're going to make a naive assumption, which is where the name comes from, the naive Bayes algorithm, that all the features are independent of each other. And this is going to allow us to represent this probability instead of by some complicated thing as simply probability of F1 given C times the probability of F2 given C times probability of Fn given C. So we can consider each of these independently. Okay, that's where the naive part comes from. Okay, and so now the really nice thing is that these things we can read right there. So if I were to say, what's the probability that you have that you're a pyro given that you're in West Campus? All I have to do is go here, and it's just 3/10. Okay, so that makes it a lot easier. Okay, so let's actually do this problem. So we're going to have the probability of being in EC, okay, times, oh, actually one more simplifying point. Since we're taking the argmax, I wrote that over here, taking the argmax, all we care about is which one of these things gave us the largest value, and just give me the C for that. So each of these expressions for each of these C's that I cycle in is going to have the same denominator of probability of all the features, okay? The features remain constant as we do this, and so they're all going to be divided by this, and we're taking a max. So we could just get rid of this denominator and take the max, and that's going to give us the same answer, okay? Because all we're interested in is the value of C that generated the max, not the actual max value. And so we're going to make that, we're going to use that to make our lives a little easier. So we won't actually have to compute this thing. So that's a little nicer. Okay. And so that's going to mean that when I put the equation up here, I'm not going to have a denominator. I'm just going to have just a numerator. And so now I can do something like this. All right. And so now we can read these three off of our table. And so I can say, okay, probability that pyro given EC is 0.8. Not languages. So they said languages is 1/10, so not languages is going to be 0.9. And then not good shape is going to be 0.7. Right? So I can multiply those out. And then what about this part? And so here's the part, you know, we can't really automate these things so well. And this comes up a lot. You know, in SVMs, we have to choose a kernel before we start. And in neural nets, in nearest neighbors, we have to choose a K for K nearest neighbors before we start. We just have to choose like this one thing before we kind of get going. Same thing here. We have to kind of choose what's called a prior, which is our prior belief of like how many people really are. What's the probability that you're in EC? Just that little probability by itself. And so in this example, they told us there were 10 people from each place responded to the survey. So we might just say there's 10 in each, so it's equally likely. So 1/3 chance, right? But you as a human actually have some control over this. You can like inject the system with some belief here. So you could say, you know, if you're in Massey, maybe there's a really high probability of being in Massey because you're like a freshman or something, right? but you could change it around. But it's really common to just think that each of the classifications is equally likely. And so since we have 3 here, this will just be 1/3. But that's where you have a little bit of control, so you can kind of enforce that. So we're going to have the same sort of thing down here, and all we're going to do is we're going to replace this East Campus with West Campus, and then with episology. So these will come from different entries, but then we'll have 1/3 on each, and we can compute the values here. And so this ends up giving us some number, and this ends up giving us some number, and it turns out that the number that comes out, this one is the highest out of these 3. And so what we're going to choose is we're going to choose the C, the classification, or the Y, so East Campus is what that person should go into. Okay. Okay, awesome. So now hopefully that gives you a good sense of what naive Bayes does. And so it's kind of weird because you don't really need to use Bayes nets to do this. So it's kind of, seems a little unrelated. But Bayes nets are actually really useful because representing something in a Bayes net is another place where you get a little bit of say. So in the same thing as how we choose how to represent this here, the way you construct your Bayes net can actually give you a little bit of say into the problem. So for instance, I might construct a graph where I think the only relevant thing about knowing whether you're course 6 is if you're a freshman or if you're a senior. So I might say, like, as a freshman, you think you can help the world out, so you're going to be like, you know, course 12 or something. But then by senior year, you want to make some money, so you go with course 6, right? So you could do something like that. I could model the world like that, but I could also model the world differently. I could not draw this, and I could have some other thing here that's like, if you're a guy, or if, I guess, guy and girl do the same thing, right? Male or female. Like, that might determine like how much you like course 6 later on, right? So I can model the world differently. And so depending on how the variables I choose and how I connect them up, I'm going to determine kind of like the structure of the problem. Another way of thinking about it is these condition tables are going to change based off these connections, because I'm changing who is the parent, right? And so as I do this, this can give me a little bit of control on the problem. Another way of thinking about it is when I have all this data, here we didn't have too much data, so we could represent it in like this nice little table. But when we get like a crap ton of data, listing it on a table might take forever. And this is where the number of parameters becomes important, which we just touched on last time. But to solve any of these arbitrary questions of like probability of, you know, y given some x, there's actually a lot of stuff you need to know. And if you don't have a Bayes net to kind of connect things up and kind of reduce the space for you, you end up having this exponential number of things you have to specify, which is a lot. But when you use these Bayes nets, I can fully specify this Bayes net. Given its topology, I only need to fill in the parameters, which is I just need one entry for each of these tables. And for each of the tables entries, I only need like one value. So there's a lot less parameters. This is not exponential. This is like, you know, I need like 10 things here because I need, this guy has 2 parents, so he's going to have 4 different rows. So I need 4 values for this one. This one has no parents, so I only need 1 value. This one's only 1 value. This one only has 2 values for depending if its parent was true or false. And this one has 2 values depending on if its parent was true or false. So that's why this stuff helps. That's why having some sort of structure on the problem and using a Bayes net like this to represent some information can help you. But, you know, the stuff that we've asked, you don't really need a Bayes net. You can just kind of use this approach and just use your like table of information and do it. So, okay. All right, so I think I've spent enough time on that. So I'll mention one last quick thing, which is model selection. So now let's say I had this Bayes net. I thought this was the best way to model the world. But you actually liked the first way better. You thought that this was a better way of modeling the world. Right? And so how do I tell which one is better? This one or this one? And so what I can do is I can take all the people's surveys. So in this table, like I said, we kind of condense stuff down and group things together. But imagine like one of the results from the survey. We could see how likely it is based off of our model of the world. Right? So what if someone said that they were a pyro, they didn't like foreign language, and they weren't in good shape. But they weren't in EC, so that's like pretty unlikely given like the thing that we made, right? So maybe that's not a good model of the world because it makes that person really unlikely to actually exist. So we do that for all the people in our survey, and we can kind of get a good sense of like, we can like multiply out all those probabilities because we assume each person like responded independently, right? So they're all independent responses. And we can kind of multiply all those probabilities together and get some probability for this thing being the right model and the probability for this thing being the right model. And just take the maximum of the two, and that's the model we choose. So this is how you go about it in practice, in case you wanted to know how to do that. But usually you don't ask too much about that, so I don't want to spend too much time talking about it. All right, so that's naive Bayes model selection. So let's jump into some example problems. So a lot of the example problems are just going to ask you to analyze, sorry, not example problems. A lot of past quiz problems, which I guess are the example problems, they ask you to analyze Bayes nets and compute some probabilities and explain if things are independent or not and things like that. So let's go ahead and do those. Are there any questions about what we just did? What I really want you guys to take away from this is, as long as you understand that we can make a supervised machine learning algorithm from this stuff, and just by that example, like, you kind of understand how we arrive at that. We don't have to do like a ton of work. That's all I want to leave you guys with there. All right. Okay. So this is from quiz 4, 2012. I'm just writing down the tables that they give us here in this problem. Okay, and then this is probability of x given m and f. This is 0.5, 0.6. 0.5. We have x big given x. Alright, so in this problem they tell us that there's a person, and we're interested in identifying this thing called gene X. This is like a bio problem, I guess. So there's a person, and this X variable stands for whether they have gene X or not. Okay? And then M is for whether their mother has gene X or not, and F is for whether their father has gene X or not. And then A is whether they develop astonishing math skills, and S is whether they lack social skills. So you can see what it's trying to model there. Okay, cool. So they give us this stuff, and then they start asking us questions about independence. So the first thing, so A1, this is worth 10 points. They have 4 true or falses that they ask. So they ask P of F given M is equal to P of F. So what do you guys think? So in other words, does it help you to know what if the father has gene X or not, if I tell you if the mother has gene X or not? No, it doesn't really help. So this is true because it doesn't change the probability. Okay. So that's a very intuitive way that we just did it. But if we wanted to do it, we'll look at the next couple of problems and we'll do them a little more rigorously because they'll be a little harder. So here's A, here's B. So just as actually this might be asking it. Okay, so just as a concept question that they don't ask this, but if I include X here, what do you guys think? Does it change? It's still the same. All right. Now, last thing. Instead of M, what if I had X? So why not? Yeah, so you could actually compute these things, and you can use Bayes' rule to move this thing around, and you can get P of f in the Bayes' rule, right? It's going to come out, and then you can kind of compare whether the other things are 1 or 0 or something like that or not. You can get that they're not. Another really intuitive way of thinking about this is think about like if it's really likely for you to inherit something only if your mom has it. Otherwise, it's not likely. So if I tell you the child has gene X, and it only happens in a likely way if the mom has gene X, then you're probably going to think, oh, the mom probably has gene X. Right? This is exactly, or the father has gene X. This is exactly what this is saying. Right? If I tell you about the kid, you might be able to make a better guess about the father. So this is the better guess with that information, and this is the guess without that information. Right? So that's an intuitive way of looking at it too. Okay. So let's move on from that. So now they ask. All right. So if I tell you about the parents of this person, and you're trying to guess whether they lack social skills, does it help you to know whether they develop astonishing math skills? That's what the question is. So what do you guys think? Yes.
Because they're just not independent. Like they both rely on X.
Yeah, so a way of visualizing that, the way I think of it is we're trying to guess this thing. So we're trying to get to like this node from the nodes that we have. So in both of these cases, we have F and M. Now F and M don't tell us about S directly. They help us make a good guess about X, right? So we know this stuff. We can make a good guess about X, and that can help us make a good guess about S, okay? But now if we have A, it can help us know X too, because X we don't know. So it can help even strengthen this guess of X, right? So what if I told you the mom and the dad both have the gene? So if you look at this truth table, when they both have it, 80% chance the kid has it, right? But then I tell you that the kid didn't develop astonishing math skills. So the parents had it, which makes you think, oh, he probably had it. But then maybe from this truth table, you think there's a really, really low chance that you can develop math skills without it. And so this might actually change what you think about X. And by changing what you think about X, you might change what you think about S, okay? So it's an intuitive way of seeing that, all right? So the way I like to do it is, here's F and M, here's S. Can I get from A to S without going through M and F? Because as soon as I go through something known, it's not helping me make a guess. I already know that. So I can go through X, which helps me guess X, and then X helps me guess S, okay? That's kind of how I think about it. All right. Cool, and then have C. So this was new. Okay, what about that one? Anyone know how to analyze this? Like, so you're saying it's wrong, but does anyone have a analysis we can use for this? Maybe we can like use some of the equations. Yeah, so we can plug in 4, which is when we switch these two things around. And then we're going to have those P of X and P of Y left over, which in this case is P of X and P of M. And so the case we're looking for, this question can be rephrased to be this one. Because these are only equal when these are equal, given rule 4. Okay? And so now are these equal? And so now you can do a little bit of math and figure it out. So P of M is given, right? And P of X, you can marginalize out the M and the F by summing over them and things like that. And so you can get the number for P of X and get that they're not equal. But in general, these have no reason of being equal, like just randomly. We have to line up these numbers pretty precisely for this to be true. So in general, this won't be true. So we can actually verify that, and we'll get that these aren't true. This is not correct. Okay. And then the last one, P of x given x a, P of s given x. So you're nodding?
Yeah, I think that it is true because as long as we know the probability, like we know that x is true, a doesn't give you any more information because that's just something that just depends. It only depends on the probability of x. There is no probability of x.
Yeah. So a can help us guess x, but we don't have to guess x. So it's not really doing anything for us. So these are equal. Okay. I want to be very clear. What if I asked you about, let's see here. Actually, it's not a good example for that, so I'll ask that later. Okay, let's just keep going then. Okay, so that was worth 10 points. So these here, and I think this is the trickiest part of the question. The rest of the question, if you have the general methods written down on your cheat sheet and you know what you're doing with that, you can get like the rest of the question right. So they ask us here, suppose Alyssa's mother expresses gene X. Compute the probability that Alyssa expresses, so Alyssa's the person who has this person, right? So suppose her mother expresses gene X. Compute the probability that Alyssa expresses gene X given only this observation. So we have to compute some probability. So how do I write down that probability? Yeah, so that's good. We need to be able to know how to do this. Now that we have this, now we can just go into the general method, and we know how to compute this from the general method. Okay, so we can use equation, the chain rule here, equation 3, to get it in terms of something that's not this given that, but rather P of x and m, and then we can also get P of m. And then for each of these two, we can use equation 2 to represent them in terms of the joint, use equation 1 to represent the joint in terms of just the probabilities of a variable given its parents, read those ones off of these tables, and we're all good to go. And we can cancel things out with the ancestor graph. So I covered that last video, so I'm just going to breeze over that. But I'm going to cover a different way of solving this problem. Another way of solving this problem is we have x given m. We already have something that looks almost like that here. We have x given m and f. So what we want to do is marginalize out the f. Right? So what we want to do is we can say this is equal to the sum over f's, so possible values of f. So f could be true or false. And we want p of x given m f, right? And so this thing, if we just write it out, is just, oh, sorry. There we go. That's sorry, I forgot this term here, to marginalize it out, because we can include things. We include things when we write this equation here, which is the second marginal one. The variables appear here. They don't appear as givens. They appear as part of like the things that we're trying to figure out up here. So this thing actually, just to see that really quickly, it would actually look like this. Okay, and then we can take this f out. We can move it back here, but we have to multiply by f here. So that's how we did that little transformation. Okay, and so now this thing is just p of f is true times probability of x given, and then we're told that the mother has it, so the mother is also true, right? So f is true, m is true, plus the probability of f is false times p x f is false. The mother is still true. And so now these ones we can just read right off of there. So true, true is 0.8. false, true. I guess they're in opposite order, so true, false, 0.5. F is false. Well, this is the probability that it's true, so false is going to be 0.9. Probability that it's true is 0.1. Add it up, and you get the probability. Okay? So that's, and they get 53 100ths. Okay, so that's worth 10 points. All right, cool. So this was 8-2. So this was a probability that Alyssa has gene X, given them that the mom has gene X. So in the next question they ask you, Alyssa later learns that her father also expresses gene X. How will the probability that Alyssa expresses gene X, given this new information and the fact that Alyssa's mother also expresses gene X, compared to the probability you computed in 8-2? So how does knowing about the father change the probability? And the options are the probability gets smaller, equal, or bigger. So let's compare these two. And these are both, this is equals true, and this is like equals true, right? There's a really cheap way of doing this. I guess not cheap, it's a smart way of doing it. We have this already. Here it is, 0.8. Oh, look, we already computed the other one. Here it is. Okay, compare them. Done, right? This one's bigger than that one. Easy. But the other way we can think about it is, I just want to cover this term so you guys have heard about it before, because sometimes they ask about it, which is called noisy OR. Okay. So what this is saying is, imagine you want to know about this person. What could cause the person to have gene X? One way you might explain someone having gene X is if you learn that their mother has gene X, then you're kind of like satisfied. You're like, oh, they probably got it from her. And then you're not like wondering where they got it from, right? Or if I told you that their father has gene X, you wouldn't be wondering where they got it from either, right? If both of them had gene X, then like you definitely wouldn't wonder where they got it from, right? It's pretty likely that they got it from there, so you're pretty satisfied with that. Okay, so this is what's called a noisy OR, because either this one or this one could have caused this one. Okay, but it's not like a perfect OR where like if you only have one, it's the same as if you had both, because we can see from this table, if I only have one, it makes it likely, but not as likely as if I had both. So it's not like a perfect OR, which is why we call it like a noisy OR, right? So this sort of thing, where knowing both of your parents like helps you out to know more, that is going to be true whenever you have this like noisy OR situation happening. So it's just like a term that sometimes they ask for. So they said like for full credit, or for credit, you must concisely explain the intuition behind the result that this thing is bigger than this thing. Okay. So if you just looked at the numbers and got it, like you still need to answer this part. And so if you just said like blah 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 noisy OR blah blah blah, you'd get full credit, right? Another way that you could probably get full credit, I would argue for full credit for this, is if you said like, well, this table tells me that having both my parents makes it more likely than having only one of my parents, and so this is like a very intuitive result, you know, or you could like explain what a noisy OR is without knowing this term, and you'd get full credit too. You know, you just have to kind of notice that. Yeah, but just so you guys have seen that term before. Okay, and then the last part of this question says, write an algebraic expression for the probability that a child develops astonishing math skills and the child's father expresses gene X. So let's write that real quick. So they want us to write an expression for the probability that someone has astonishing math skills and their father has gene X. So if you have general method written in your notebook, this is the question you want to see on the exam, because this is exactly what it tells you how to do, right? So how would we do this? So whenever you're stuck, look at those four equations and see what you've got. So do we have the entire joint probability with all the variables? No. Okay. Do we have a marginal probability where it's an and of a lot of the variables but not all of them? Yes, that's what we have. Okay. So now we can use equation 2 to make this look like a sum over the things that we don't care about. So we can sum over everything that's not A or F. So we're going to get M, X, and S. Okay. Over the joint probability. Okay. Now we have this thing. We have the joint probability, so we're stuck again. So we look over there, and we say, okay, do we have the joint probability? Oh yeah, that is what we have. So we use equation 1. And we're going to get the sum over M. So I could write this as 3 sums, same thing. M, X, S. And now what I'm going to do is I'm going to express the joint as a multiplication of a variable given its parents. So I'm going to say probability of A given its parents, so it just has X, times the probability of F. I'm just going to iterate through them. F times its parents, it doesn't have any, times the probability of M times its parent, given its parents, it doesn't have any, times the probability of X given its parents, it has M and F, and then the probability of S given its parents, which is X. Okay. Now we use the ancestor graph. So the ancestor graph says, these are the things we care about, A and F. So circle them. And I've kind of already circled these, but pretend I hadn't circled those. And now the ancestor graph says, only consider ancestors of these nodes and the nodes themselves. So A and F for sure. Okay, now can we reach X by going up from one of those? Yeah, we can. Right? Can we reach M by going up from one of those? Yeah, we can go up twice. But can we reach S? No, we can't. And so we're going to get rid of anything that has to do with S. So get rid of this thing, get rid of this thing. It's like the quick and dirty way of doing it. There's like reasons for this, right? We do this because we can like push this sum all the way into here, and then when we sum over that thing, it just ends up being 1, and then it gets multiplied, and it's just like 1 times something. So it's not useful. But this little like ancestor graph trick can help you not have to do that. So that's nice. Okay, so we just get this thing. And now it's a lot easier. In fact, we're done with the problem because they just said to write an algebraic expression, not to actually solve for it. But we have it in terms of the probabilities that are given here. So that's kind of what they wanted, the algebraic expression in terms of the probabilities given in the conditional tables. Okay, there it is. So that's how you do that. Okay. All right. And then, okay, so I'm running out of time, so I won't cover the last part, which is worth the last 10 points. But again, if you know how to do the general method, you will get this problem. It just asks you, like, it gives you a bunch of probabilities, and then it asks you, like, what is this probability? And then you just use the general method and solve for it. Sometimes they won't give you, like, the full table. They'll give you just some of the probabilities, so you might not be able to use the general method. You might have to, like, look at these equations and see what you need and what you don't have and use those. But as always, if you ever get stuck, just look at those and see what you have and what you need. And you can kind of force your way in to get something in terms of only the probabilities that you have. Okay. And then last thing, just some terminology. This is prior and posterior. So I mentioned this prior before. Intuitively, what this is saying is like a probability over some variable given no information. So given no information, if I have to give you a number for this like variable that I don't know anything about, it's just going to be like my best guess, like what I think before I even start the problem. That's why it's called like a prior. It's like prior to the problem. This is like my belief of the probability of this variable, right? And then posterior is like after, right? Post the like doing something, you might have a different idea. You might update what you think about that variable. So just saying, given some information, given some tests you did, you might now make a different guess over what this data is, right? So these are just two terms, and that's like intuitively what they are. But honestly, I think if you know what this is and what this is, you don't need to necessarily know the labels. You can do all the problems. So I wouldn't worry too much about this. All right, that's all I got for you guys.